So now that we know about how to measure the Earth and how to locate things on its surface, let's discuss how the world becomes a flat map using projections. A projection is a systematic transformation of the three-dimensional Earth onto a two-dimensional developable surface. All projections include distortion, and not one projection is the best universal projection for all purposes. In this lecture, we'll talk a little bit more about map projections in general. So back to the first video. The problem that cartographers have is that when you take a sphere or spheroid and try to lay it out flat, something's going to give. Just like taking an orange peel and trying to flatten it out, something gets distorted and it's virtually impossible to do it without breaking the surface into at least a few pieces. Any projected flat map or parts of a map can have the following characteristics: true direction, true distance, true area, and true shapes, or DADS. Maps typically can't have all of these characteristics at one time. So when you choose a projection, you are deciding which of these characteristics you want to retain or that will have the least amount of distortion. As such, we can use these properties to describe a projection's distortion. At least one or up to all four of these properties may be distorted on a projected flat map. Typically, projections are named based on the characteristics that they maintain. For example, maps that have true direction are called azimuthal. Equidistant maps have true distance. Equal area maps have true area. And conformal maps have true shapes. So when you have a Lambert conformal conic projection, you know that it's best when you need true shapes. Other characteristics will be distorted to a greater extent. The distortion also depends on your developable surface. A developable surface is a surface that can be flattened onto a plane without any distortion. That means there's no stretching, no compression. Depending on how we flatten the Earth and which projection type we use, the developable surface will be different. If we use a plane, we have a point of tangency, and the areas touching the plane are not distorted. If we use a cylinder, any location that is tangent or secant to the sphere or touches the sphere perfectly will not be distorted. Finally, if we use a cone to flatten the Earth, an area that is tangent or secant to the cone will also not be distorted. In all of these examples, there's only one point or one line, depending on the method that we used, in which there is no distortion. As you move further away from the point or line, the distortion increases. We use the developable surface to classify different types of projections. Let's look at different types of projections more closely. Back to our Lambert conformal conic projection. The conic means that the developable surface of this projection is a cone, and the parts of the world that are least distorted are along the standard parallels or points of tangency indicated here. Not all of the names are this easy, but there are plenty of resources out there that list projections and their distortions. Let's look at cylindrical projections. Imagine placing a movie screen around the globe in a cylinder shape. The projection results in areas very close to the equator having very little distortion. However, closer to the poles, the area is more distorted. For example, Greenland appears to be many times larger than it really is. One of the most common cylindrical projections is the Mercator projection. The Mercator projection is conformal, tangent lines along the equator, and has straight lines. There is no convergence at the poles. This means that along the equator the distortion is minimal. However, as you move further away from the equator, either north or south, the amount of distortion increases. This type of projection is very useful for navigation. At or near the equator, any straight line drawn is a true compass heading, otherwise known as a room line. It is truly a directional map. A conical projection is created by placing a conical-shaped screen on a globe. The resulting semicircular map is more accurate than a cylindrical projection map. The further we travel down the map, the more distorted and less accurate the map becomes. Conical projections are used for mid-latitude areas that have an east-west orientation. They're very useful for projecting areas such as the United States, which is mid-latitude and has an east-west orientation. The lines of latitude where the cone touches the Earth are called standard parallels. Azimuthal or plane projections are created by placing an imaginary screen directly above or below a globe. While not commonly used, it retains area, direction, and distance properties. Because of this, it can be useful for maps showing population density, political boundaries, oceanic mapping. As you can see from these examples, azimuthal projections have a point of tangency compared to conical or cylindrical projections, which have lines as tangential points. This means that there's only one point that minimizes distortion in an azimuthal projection. There are many different types of interrupted projections. They tend to depict continents as accurately as possible by leaving a blank or empty space and less important areas such as oceans. So the ocean may be cut out of the map, but the land area will be more accurate. These types of projections are often called orange peel maps because they distinctly resemble that flattened orange peel we looked at earlier. Interrupted projections can be used for equal aerial world maps and are used very commonly with raster data. The United States Geological Survey Center for Earth Resources Observation and Science Center provides data in Goods Homolocene projection, which is an interrupted projection. So with all these choices, how do we decide? In the next video, we will look at ways your GIS software can help you with projections.